Hello kids, today we will be discussing thermal properties and temperature. That would be topic 2.1 and 2.2 from your content. This is the thermal block. We'll start with the thermal block and we'll try to end it as a whole, right? So let's get into it. Uh, First of all, we need to understand what temperature is, right? So let me get the ball pen. So what is temperature, right? Temperature. We can define temperature as the change in energy of a material. So what is change in energy and what kind of energy we are going to relate with this temperature, the energy that we call as heat, right? So what do we mean what do we mean by this, and how do we understand this? So for this we have the kinetic theory. So the kinetic theory suggests that whenever the particles are there, I mean, we do know that all matter is made up of smaller particles, right? Atoms or molecules. So they are always in motion, right? And since they are in motion, that means they have certain kinetic energy, what we represent as EK, right? So and we do know EK is 1 by 2 mv square. That means when there is some movement, when there is some velocity, we can relate that to the kinetic energy. And since the particles are always in motion, that means they have a certain kinetic energy. And that energy is what we mean by the internal energy, or the energy that these particles have with which they are all in constant motion, right? Now, we can relate this energy with the temperature, that if we increase the temperature or if we heat that matter up, we would find that the speed of these particles is increasing. Why? Because when we give it heat, we're giving energy to these particles, right? And when they have more energy, that energy will be translated in terms of speed. Why? Because mass does not change. The mass of the particle won't change with energy, right? Mass can neither be created nor be destroyed. That's the law of conservation of mass. So we're going to stick to it, and we're just going to convert or translate this change in energy as a change in speed of this particle, right? And when we say energy, we can simply call that kinetic energy of these particles as the heat, or the internal energy of these particles, right? So the more the energy that these particles have, the faster that they will move, right? So if we start increasing the energy, right, we will find that the temperature also rises. So we can simply say that the change in this energy can be measured using the change in temperature, right? We simply relate energy to temperature. So we say what is temperature? It is a measure to calculate the heat that an object has, right? But we cannot measure the energy using a constant temperature, so we need to have certain change in temperature to be able to measure this energy, right? So once we start heating something, we actually measure that change in heat, whether it's heating or cooling, with the changes in temperature, right? I hope this clarifies some of the confusion, that what is temperature and what is heat. These are related terms in which the temperature is the method to measure this heat or energy, right? Okay, now let's look into another factor. What is transfer of energy, right? So imagine we have one object which is at higher temperature, and we have another object which is at lower temperature. Now we always know that energy flows from a higher to a lower gradient, right? So over here, this is the higher gradient, right? And this is the lower gradient. So once we join these two objects together, uh, the energy of these high energy particles will be transferred slowly into this low energy object, right? And why? Because these particles which are at higher speed will start to collide with this barrier and transferring their energy to these low energy particles, right? Up to a point when both these objects will have same temperature, right? uh, till that point is reached, the energy will keep flowing from the higher to the lower till both of these are at the same temperature, right? So uh, the average kinetic energy for both these particles would be same after the temperature has become same, right? So as I said, we can always relate temperature to the energy of these particles. Moving on, uh, are temperature and heat the same? No, because we understand that temperature is just a measure of this heat, right? But how much heat is actually there, it depends on several factors, and the biggest factor is mass, right? So we need to understand that energy is related to mass, right? And we do know this from EP, right? Potential energy, that is also dependent on mass, right? uh, Potential energy is mgh. So the greater the mass, the more the potential energy. Let's say if I drop an lighter object, the impact that it would have would be less compared to a very heavy object if I drop it from the same height, right? So the mass does affect the amount of energy that an object is carrying, right? Similar way, if we have kinetic energy, right? In even in that case, we do know that it is half mv square, right? So again, the mass does take account, right? It is accounted for, right? So that means, let's say if I have two vehicles, one is a smaller one and the other one is a heavier one, we would find that the heavier vehicle, both moving at the same speed, will have different energy. The heavier one will be harder to stop, while the lighter one would be easier to stop, even though the velocity was the same. But since the mass was different, so the amount of energy required to stop them would be different, right? So we do know that energy is affected by the amount of mass that is there for an object. So let's come back to our question. Are temperature and heat the same? No, they're not. For that, let's look at this example, right? If you have a spoon of boiling water versus a beaker filled with boiling water, uh, let's just say somehow you get to spill it on your hand, right? This would be damaging, but not as much as this would be, right? Why? Because this has more mass, so it has more energy that it can deliver to your hand. And this, since it's a spoon full of boiling water, so it might cause some damage, but not as much as this beaker is going to do. Because why? There's more mass, so there's more energy to account for, right? So we can surely say that heat is very much dependent upon mass, and by heat we mean energy, right? So let's move on to the next idea, which is thermal expansion, right? And what is thermal expansion? By thermal expansion, we mean that whenever we heat something up, that matter expands, right? So let's just say we have these matter particles. Consider this as a solid, right? As you can see, if this was the whole area, now over here, after heating it up, the area has increased. Why? Because these particles, which were vibrating for a solid, as we know that solid particles can only give or only have vibratory motion. In this case, the amplitude of the vibration, that means as you can see, the gap over here has increased compared to this one, which has a larger gap, right? And why is that so? Because these particles are now moving this much, right? Compared to this small little vibrating motion. So from hot to cold, from cold to hot, we see that matter is expanding, right? Now this is an example of a solid, right? So in solids, let's list it down, right? Different materials expand at a different rate. So that rate of expansion is what we call as the coefficient of expansion, that how much a material would expand depending upon by changing a certain degree of temperature, right? So we see that glass expands little bit, concrete expands somewhat, right? Brass expands quite a lot, steel doesn't expand much, but aluminum expands a lot more, right, than all of these. So whenever we're considering this fact, we need to understand that if we're using a material for a high temperature application, we need to consider the coefficient of expansion, right, before we consider any of these materials to be used in our design, right? So as a design factor, coefficient of expansion is a really important coefficient to discuss. For example, if something is to be used at a hot temperature, then we need to account for the coefficient of expansion. We need to give some tolerance for the expansion. Otherwise, the material may collapse or it may get damaged if we do not allow that material to have enough space for expansion. For example, if I'm supposed to make a key for a lock which is operated at a high temperature, right? So I can make a key out of steel because it doesn't expand much. But what if I make the key uh, using aluminum? So as soon as I insert this aluminum key into the lock, since it's at higher temperature, the lock is at higher temperature, aluminum would start to expand, and that may cause the key to either get stuck in the lock, or it may not be able to operate the lock properly, because since aluminum expands a lot more than steel, that means it is going to be harder for the key to operate the lock, right? It may not even operate the lock at all, right? So we need to account for thermal expansion of materials before we go into using those materials at any temperature, any specific temperature, right? So we need to understand what is the thermal expansion at that specific temperature, right? Okay. That is just for the solids, but we need to understand that all matter expands when it heats up. Why? Because as we said that when we heat something up, we give it energy, and when we give it energy, we're increasing the velocity, right? V square from the kinetic energy. So we're increasing the velocity of these particles. In other words, we're increasing the amplitude of vibrations for solids, and since in liquid and gases particles are able to move randomly, not just that they have vibratory motion, but instead they're able to move around freely. So that means liquids are going to expand a lot more than solids, and definitely gases will expand a lot more than liquids. Why? Because the particles are much more farther away. So if I consider a solid, then the particles are very much packed together. In liquid, the particles are still packed together, but they are not having any intermolecular forces in between them, not much, not very strong. So by increasing the temperature, the particles starts to bounce around, or they move around faster. In terms of gas, the particles are already farther apart from one another. They do not have any intermolecular forces. So if I increase the energy, they will move a lot more faster, and definitely that will cause expansion to be a lot more compared to the liquid. So if I discuss the rate of expansion, then I say that the gases expand more than the liquids, and the liquids expand more than the solids, right? So this is how the hierarchy of the expansion works, right? Gases expand the most, liquid expand quite a lot, but solids, they don't they tend to expand a little bit less as compared to the previous two, right? Now moving on, uh, how can we observe thermal expansion, right? Now this is one example of a experiment that can be done to understand how thermal expansion actually works, right? So we have a steel bar in which we have a cast iron peg, right? And if we try to heat this rod up, we would find that the metal bar is going to expand, right? Since at this point it is fixed, right? It is framed, so this will try to expand, and once it will keep on expanding, this peg is going to block this expansion, right? And if we keep on expanding this rod, this peg will be broken down, it will be snapped, right, into pieces. Why? Because this rod needs to expand, and this experiment definitely shows how strong these thermal expansion forces are, because the particles are expanding at a local level, so they will exert a huge amount of force while expanding, right? So anything that comes in between will be broken down. So you need to understand that previously, this what we discussed, that the coefficient of expansion needs to be understood. You need to understand that if we create any structure using a material, any material, and if we don't account for the thermal expansion, then in summers it may be a collateral damage of some sort, right? It may cause some structural damage due to expansion, right? So we need to understand that this is a very important factor to note, that materials expand, matter expands when heated up. So if it's a high temperature application, we need to account for the thermal expansion, and we need to give gaps like these to have thermal expansion to be understood. So if there's less temperature to be dealt with, then the gap is fine. But if we have very high temperatures to deal with, then we need to understand that we need to give more tolerance of expansion, so that this peg along with the rod would move quite a lot more, right, during expansion. So we need to give space to this peg, right? This is a very crude example that how we need to account for expansion and what we can do to prevent any damages due to thermal expansion. So we need to give tolerance, so that if we use any structural material like the steel bar, we need to give space for things to expand so that they don't snap off, right? Now moving on, thermal expansion, right? Now girders, right? These are the bridges, and these gaps are placed in bridges. And why these gaps are placed, I mean, you must have been in a car crossing over bridges, and you find that they have these bars, metal bars across, right? And why they place these bars over there? Why? Because during summers, even concrete expands, as we saw over here, that concrete does expand, and it does expand greater than glass or steel. So we need to understand that when we make concrete bridges, we need to have some gaps in between them, right? As well as at times we use these rollers at the edges, so that if it expands, it is not fixed in a way that it doesn't break, right? If this bridge expands and we don't give any space, these tiny little slits in the bridge, then or these rollers, right, by keeping this end open, right, or this end open, we need to understand, if we don't do this, then the bridge may collapse, and that would be a very, very dangerous thing to have, right? So that is why you will always find either bridges having these metal bars, or if it's a stiff bridge, if it's a bridge with without these metal slits in them, right, or these gaps in between them, then you would find that if it's a small bridge, then you will find there are rollers as well as an open end at one corner, right, of the bridge, which will allow this gap to have the expansion, right? Similar way, even the aircrafts, they expand. So in these aircrafts, we need to account for for expansion. So whenever an aircraft is built, we need to understand that we use design strategies in which thermal expansion is accounted for, right? Similar way, during the cold summer, if we look at these metal cables, if you see these, right, somewhere with these big pylons of electricity, you would find that in winter they appear to be very stiff and very straight, while in summer they tend to lag a little bit. And why is that so? Because these high electricity cables, high voltage cables, which are usually overhead with the large pylons, right? We see some of these in our own society, right? You've seen these large ones right in the middle of our society. Now, we do know that aluminum expands quite a lot, and these electricity pylons utilize aluminum wires to conduct electricity from the grids to the different sections of our society. So you need to understand that during summers they tend to bow a little bit. Why? Because aluminum is expanding, and these pylons, they have a fixed gap between them. Then aluminum definitely needs to bow a little bit to account for the expansion that is there during summers, right? I hope this covers a little bit of the thermal expansion, right? Moving on, what are the applications for thermal expansion, right? The most basic is the thermometer itself, that we use this idea of thermal expansion to identify the temperature of any unknown temperature material, right? Let's say if we have a beaker of water, then we can use some kind of a thermally expanding liquid or a solid. And why liquid? Because we just reviewed that liquids expand more than more than solids. So we can say that we can safely use liquids like mercury, which is a metal but it's a liquid, or alcohol, which you would find in the blue or red color of these thermometers that you find in the market, right? For your, even in the lab you have these red ones, right? So those are alcohol based expansion thermometers. So these thermometers, when there's a change in temperature, right, the the liquid level, let's say if this was at 0 degrees Celsius, so when the temperature rises, this liquid level is going to rise up, pertaining to the amount of heat that is there or the temperature that has been attained, right? Let's say this is at 50 degrees Celsius. So at 50 degrees Celsius, you would find that the level of alcohol or mercury will rise from this point to this point. And this is a crude example of thermal expansion being used even in temperature measurement. So as the temperature rises, the liquid in the bulb will expand, and so rises up the narrow tube, which will be calibrated, and we can calibrate it using known materials. For example, we do know that at frozen, when water is being melting off from an ice cube, we can just put a thermometer on an ice cube. Whatever the level is, we just mark it out as 0, right? And when we start boiling it, when we see that boiling has started, we can mark that upper temperature as 100 degrees Celsius. This is how we can calibrate. And what calibration means: to specify the limits, operating limits of an instrument. That is what calibration means, right? So we can simply calibrate even an unknown thermometer. So we can make our own thermometer. If we have a little bit of alcohol, we use a glass capillary. We make a glass capillary bulb at the end. We close off that end, and we may even leave the other end open, and we simply just put that glass capillary in an ice cube water, and we can mark the lower level of the alcohol as 0. And once we start heating that beaker up, the upper level can be marked as 100, and then we can calibrate it as a temperature, right, as a thermometer. So we can literally build our own thermometer in the lab. Now another example of thermal expansion is the bimetallic strip, right? We use this as a mechanical switch, or even as an electromechanical switch, right? And what is a bimetallic strip? It is a metallic strip made out of two different metals having two different thermal expansion coefficients, right? Over here we have one piece of metal which has a higher expansion rate, and the other one we have a lower expansion rate metal, right? And we simply join them together using any fixture or any specific method, right, riveting or something. And once we start heating it up, we would find that the upper layer, which expands more, would try to expand a lot more, right? And the lower metal won't be expanding as much as the upper one. This would cause this bimetallic strip to bow. Why? Because the forces will create a torsional effect on this bimetallic strip. Why? Because the lower strip is restricting the expansion while the upper strip is trying to expand. As a result, it would try to incorporate the expansion in terms of geometric changes, right? And in that case, we will find this metal to be bowed. Remember, it is always the higher expansion rate that would have the bow, and the lower one will be the one which is bent inward, right? So this way we can simply identify which one is which metal. Let's say if I give you a question of this diagram, I give you this diagram, ask you which metal out of the two, metal A and metal B, will have a higher expansion rate, then you need to understand the one which is bent outward, right, is going to be the one at higher temperature expansion, right? And the one which is at the bent inwards will be having lower expansion coefficient, right? So this way we can simply identify just by looking at the geometric changes of the bimetallic strip. And this bimetallic strip, as I said, can be used as a mechanical switch. Let's say to have a mechanical switch to operate something, or as an electrical switch, let's say in terms of our you know ironing of the clothes, right? We have this setup in our iron, right? When we are ironing the clothes, we set up a specific temperature. That temperature sets up the base level of this strip, and once the current goes through this strip, right, we do know that the iron gets heated up, and when it heats up, it automatically turns off. Why it turns off? Because at a certain point of temperature, that depends upon the setting that we're using it on, right, this bimetallic strip is going to bend downwards, right? Since this one end is riveted and the other end is free, then this will expand more and the lower strip will not expand as much, so we will find that it would turn downward. As a result, this contact will be opened, right? So at a certain temperature, this bimetallic strip is going to break off from this electric contact. As a result, electricity will stop flowing, and no more heating would be there, so it will prevent overheating of the iron. Hence, you're not going to burn your clothes while ironing those, right? So so keep in mind that it's this bimetallic strip that helps in keeping your clothes safe while you're ironing it. Now these are available in all modern day you can say irons, as well as in the previous ages, like back in the 1980s, these bimetallic strips were not that very common, and people used to have those ironing tools which were not having these bimetallic strips, and most of the time if they keep the electricity on for too long, that it may burn the clothes while ironing. So this bimetallic strip saved a lot of clothes in the process of ironing. So bimetallic strips may be used as thermostats. What's a thermostat? It's a as I said, it's a mechanical switch that operates any device. One is also available in your geyser, right? Water geyser, water heaters usually use these bimetallic strips as a mechanical switch, because electric switch may fail, but these metallic switch, they can go many years before they need any maintenance or replacement. So it is very easy to maintain, right? You just put it in, and it would remain there for many years before it needs any replacement, right? uh, Moving on, thermal expansion. Now we're going to look at an anomalous behavior of water. Now water, we do know that if we heat something up, it expands, right? But in case of water, we have a specific range in which water is actually going to contract and then expand over again, right? So that's the mysterious behavior of ice. As we do know, if we heat something up, it will expand, and if we cool something down, it will definitely contract, right? It's the opposite way around. It's just vice versa. But in case of water, we have something different, right? If we keep on cooling water, we find that it is shrinking, right? Water does not expand, right? I mean, in heating it does. When we're cooling, it is actually contracting. But for a specific range, and once it's turned into ice after cooling, when we freeze it up, we see that ice is floating. And what do we mean by float, right? We do know from the density experiment that anything that floats on water has a lesser density than water. And if we have a floating ice, that means frozen water itself, right, is having lesser density than liquid water. And why does that happen? Now we need to look into this idea. So we're going to look deeply into the atomic structure. So when we look at liquid water, we see that these particles are very close to one another. They're able to move about using random motion, right? They move with random motion, but they can simply slip over each other. So even though they are close to one another, they can simply slip over, right, during the random motion. But once they start to convert into ice, right, that's where the fun begins. When we see these turning into ice, these water molecules, they actually form these intermolecular bonds as well, which creates these hollow spaces in between these structures. These hollow spaces or air gaps are also there, as you would find that if you have a ice cube, if you try to solidify water, you find that some of the air is still entrapped as well in there, right? Some bubbles are there at times. This shows that water during freezing expanded, right? And why it expanded, that this is the anomalous behavior in which when water was in liquid form, the particles were much closer to one another compared to ice when the particles are quite farther away from one another. And this is due to this specific arrangement of particles in ice, right? So, does ice float on water? Yes, it does. Why? Because it has lower density than liquid water. And why is that so? Because in solid water, what we call as ice, the particles have a lot more spaces in between them compared to liquid water. So, this is the mysterious behavior of water while we're understanding the concept of thermal expansion. So, water does expand when it's heated up, and it contracts back when it's cooled down, but for a very specific range, it does the opposite, right? So that range is actually from 4 degrees to 0 degrees Celsius, right? So during this temperature, the water actually expands slightly, causing the ice to be on top of water rather than sinking inside water. So we can see this happy penguin sitting on ice because ice is floating and he doesn't need to take a swim, right, in the cold water. He can just simply float on ice and take an ice, slide or whatever. So when we're discussing this, you need to understand that ice will float due to this anomalous behavior, and the temperature range for it is actually from 4 degrees Celsius to 0 degrees Celsius. When we're cooling water, it actually expand, which is a very odd behavior we don't get to see anywhere else, right? This is a very unique behavior of water, right? Moving on. Thermal expansion of gases. Now, in terms of solids and liquids, since we do know that solid and liquid have a definitive volume compared to gases, right? So when we talk about solid and gases, we say they have solids, they have definitive shape as well as definitive volume. So that does not change, even if if we do change the temperature, the volume is going to change a little bit, but the shape may not change much, right? But in terms of liquid, we don't have a specific shape because the liquids take the shape of the container, but it does have a specific volume, right? Which may expand a little bit with heating. But what about gases? As we know that gases can take up space, whatever space is provided to them, right? So we can fill up a tiny little test tube with a gas, and the same amount of molecules can be spread out. If I open up that test tube and let it float around, let it be open in the room, those particles will be spread all across the room, causing a very unique behavior of gases, in which the volume of the gas to not being constant. It only depends on the container that we have. So whenever we're studying gases, you need to understand we need to keep them in a certain container to understand their volumetric changes, right? Now, to have any study of the gases, we are going to fix this up. So this is a fixed container in which we have this gas, right? As we heat it up, we would find that the particles of these gases are going to have more energy, and when they have more energy, they will have more speed. And when they have more speed, that means the momentum with which they are going to collide with the walls of the container, what we call as the pressure, right? The collision of particles with the walls of the container is what we call as gas pressure. So that will start to increase. So once we start heating up, we will find that this pressure gauge needle will keep on moving towards the higher end. Why? Because more energy, more energetic collisions, that means more pressure is being built up. So when I say gas pressure, that means pressure of a gas is actually directly proportional to the temperature that is there. So as we do know that temperature is the measure of energy that these particles are carrying. So since we're changing the energy, when increasing the energy, we can measure it by the change in this temperature, right? So we can say the change in temperature will respond to change in pressure for a gas, right? This is for gases, but at constant volume, right? Why? Because if we let this object to float around, we would find that by increasing the pressure, these gas particles will push this upper barrier and will increase their volume, compensating for the pressure, right? But if we fix the volume, then these particles do not have anywhere else to go, or release their energy, so they're going to keep on hitting the walls with higher energy, causing the pressure to increase. So remember, when we say that pressure and temperature are relatable, then we need to understand they're only directly proportional when the volume is consistent, the volume is fixed, right? So we need to fix this top lid of this cylinder in which we have contained the gas, right? So when we heat something up, we need to understand that the pressure and the temperature can be plotted around as a straight line, right? The greater the temperature, the greater the pressure, and we can work this all the way back up to a point where we have this absolute zero temperature, which is minus 270, roughly minus 273 degrees Celsius, which is 0 Kelvin. At that, the pressure is supposedly zero. That means these particles will no longer be able to move around. That means even gas will be solidified at such low temperatures, right? These particles will no longer be able to impact anything. And if we keep on increasing the temperature, we would find that the pressure is increasing. So we do know that hot air balloons go up. Why is that so? Because the pressure inside that balloon, right? Light particles or high temperature particles, they move up. Why? Because they have higher energy, so they would tend to move up. They have more pressure as compared to the atmosphere. That is why they will try to move up. So that is another example of why temperature changes will result into pressure changes, right? Hot air balloons, that's another example for this. Okay. Thermal expansion of gases. Let's continue and let's discuss what absolute zero temperature is. Now I've discussed this quite a lot in the class, that what absolute temperature is, and we're going to relate that. We do know that let's draw a number line. This is 0 degrees Celsius, right? So in the early days when we discovered temperature scales, we only had ice and we only had water to work with. So we understood that temperature usually varies from 0 to 100 degrees Celsius, at which water boils and water freezes, right? This is the freezing point and this is the boiling point of water. But later on we came to know that things can be colder than water, and that is when we understood that this 0 degree Celsius scale is not absolute, it is relative. Why relative? Because absolute scales are those scales in which there is no negative value, right? So definitely the absolute scale for temperature is Kelvin, in which it starts from 0 Kelvin. Right now I'm going to draw another line, right? I'm going to change the color. Now I'm going to draw another scale, this blue one, alongside this Celsius, and I will call this as 0 Kelvin, right? And at 0 Kelvin we do understand the temperature of the gas is going to be minus 273 degrees Celsius, right? That's the conversion for degrees Celsius to this. So this is minus 273, right, degrees Celsius, which is equal to 0 Kelvin. And consequently, if we keep on increasing the temperature, we find that at 0 degrees Celsius, which is the freezing point of water, the temperature in Kelvin is actually 273 Kelvin, right? So it is just an addition of 273 when we're jumping from degree Celsius to degree Kelvin, right? Now, since we have discussed this a little bit more, you can review, you can read through this slide and get a better idea. Now I'm going to keep moving forward because we have to cover a few things in which pressure law is very important. And we just discussed the pressure law previously, that when we have a fixed volume of a gas and we increase the temperature, the pressure is going to rise, right? So for a fixed mass of gas at constant volume, the pressure is directly proportional to the Kelvin temperature, right? And why Kelvin temperature? Because we just discussed this, that 0 degrees Celsius, at 0 degrees Celsius we do have gases that have a certain pressure. That means pressure is not zero. That means furthermore we can reduce the temperature, and that's what we see when we draw this line backwards, when we draw this trend, that zero pressure is only attainable at minus 273 degrees Celsius, which is absolute 0 Kelvin, right, over here. So with this we can actually relate that in a sealed container or constant volume, right, now pressure and temperature, the change in pressure or temperature is a constant, and that constant is actually the volume, right? So I can simply say that the ratio of the pressure and the temperature relates to this constant. And if we have two states, let's say before heating and after heating, so P1 T1 should be equal to P2 T2. That means the change in pressure and temperature before heating should be equal to change in pressure and temperature after the collision, right? This ratio will remain the same because the volume is fixed, right, since the container is fixed. So let's look at an example. A sealed container has a volume of 25 liters. Sealed container, that means a fixed container, right? The gas inside it is at 1 bar or 1 atm and a temperature of 300 kelvins. What will be the pressure if the temperature is increased to 325 kelvins, right? So if we use this pressure law, right, which we call the Boyle's law, right? So we're going to use the Boyle's law and discuss that the pressure over temperature, that is 1 atm over 300, should be equal to the pressure in atms divided by the new temperature, the increased temperature. So this ratio will be 1.08 bar or 1.08 atms, right? So that's a quick example for what pressure law is supposed to work like, right? We can use this to calculate different pressures at different temperatures of a gas, right? But remember, this is for fixed volume. Now we can also relate volume and temperature by keeping pressure as a constant. So previously we kept volume as a constant, and now we're going to make pressure as a constant. And what we can do is that in this case over here, when we had this fixed lid, now we're going to make this lid movable, but we're going to put a weight over here which is fixed. Let's say 1 kilogram of a block, I place it over. That 1 kilogram block will have a specific pressure, not more. I mean, 1 kilogram is only going to exert a specific amount of pressure onto this lid, right, compressing the gas. So it will allow the gas to expand if these particles will have more drastic collisions with the lid, right? So the lid can now move upward and downward depending upon how energetically these particles are colliding with the lid, right? But since the weight is constant, the mass that we're using is constant, so the pressure will be constant, as we do know that pressure is force over area, right? And we do know that force can be translated as weight of an object, right? So we do know weight is mg, mass into gravitational acceleration. So again, mass. So if we fix the mass, then we fixed up the weight. That means the pressure is now fixed, right? So Joule's law, it dictates that at a constant pressure, we call this as isobaric, right? Isobar, and by bar we do understand that bar is a unit of pressure, right? We just discussed that atm or bar, I mean that's isobaric, right? So isobaric pressure. So I'm going to use three terms more frequently. One is isobar, that means constant pressure. Then we have adiabatic, that means constant pressure. Adiabatic, this is a term used in physics to discuss things at constant volume, right, especially gases. And then we have isothermal. Iso means same and thermal means temperature. So we have three terms: adiabatic, right, isobaric, and then we have isothermal. So three terms you need to look up for in physics, and you need to memorize these three terms. That isobar means constant pressure, adiabatic means constant volume. They may not tell you that it's a sealed container. They may just dictate that a gas, an adiabatic gas of this much volume is undergoing a temperature change, right? So they can write the question like this as well. So what is Charles' law? For a fixed mass of gas at constant pressure, the volume is directly proportional to the Kelvin temperature. Now remember, over here, fixed mass is also a very important factor, right? In both the cases, which I actually missed to discuss, that we cannot change the mass. So, and why cannot we change the mass? Because the gas was entrapped inside, so definitely the mass is not going to change for the gas. So when we discuss Charles' law, we need to understand that the pressure is now constant, mass is must to be constant. Definitely if we increase the quantity of the gas, then definitely all the variables will change drastically. So mass is fixed, that's a key element. So at constant pressure, the volume is directly proportional to the temperature in kelvins. That means V by T, right? The ratio of the volume and the temperature should be a constant. That constant we have just discussed, that's the pressure, right? So V by T is equal to constant. So V1 T1 V2 over T2. The initial state and the final state should be the same. That means if the gas, let's say if the cylinder was here at T1, then at T2 the volume should be here, right? The lid will rise up a little bit. Now don't mind if the if you see the difference in this. I'm just doodling around with this. Okay, so the temperature change will induce a change in volume. Why? Because the pressure that we're applying on it, the weight that we have on it is same, right? The mass is same. This could be mass, or this could be just the atmospheric pressure, right? But again, at atmospheric pressure we cannot hold up a gas in a container, right? It would just move out and escape our container. So we need to keep a lid with a fixed mass on it, so that the gas does not escape our container. So let's look into an example. A gas at a constant pressure has a volume of 22 liters with a temperature of 280 Kelvin. What will be the volume be if the temperature increases to 320 kelvins? So again, V1 T1 over V2 T2 should be equal to, please don't mind this second is equal, right? Should be represented as 22 by 280 V2 over 320. So the volume is going to be 25.1 liters. That means there is an expansion in the volume, right? It was 22 liters before, and now it is 25 liters at higher temperature. So definitely the change in temperature will result in the change in volume. That means greater the temperature, the greater the volume, pertaining to the fact that the pressure is kept constant. Again and again, when we're discussing volume and temperature, the pressure needs to be constant, and when we're discussing pressure and temperature, when we're discussing volume and temperature, the pressure needs to be constant, and when we're discussing pressure and temperature, the volume needs to be consistent, right? And by law, we can actually combine these two laws together, but that's what we do at a later stage, but we're not going to go into that for now. Now some examples of temperature measuring devices, right? Just as a heads up, what we can use to measure temperature. We have thermometers. Some of these are clinical thermometers, right? Then we have these electric modules to measure temperature, what we call as thermocouples, right? Or RTDs, resistance thermometry, right? So there are many ways in which we can measure temperature. So these are few devices. Then we have the lab-based thermometer, which looks just like this one, right? We even have a digital thermometer in the lab at the moment, right? Which has a wire instead of this fixed one, right? This sensor, or the RTD, I just said, resistance thermometry, right? That is actually connected to this digital module using a wire. This is a fixed one. The one I'm using has a long wire, right? So it gives a digital reading on this gauge, right? We can just read it out. Over here we have to locate what the volume is, then we check the level of the expansion, and then take the reading of the temperature, right? So these are few devices that we can use in our daily life to measure temperature. Thermocouples are actually used more in the industry, and these are more daily life examples which we can have. Both of these we have in the lab. These are more specific, for industry. Okay, moving on. A very fun concept: boiling versus evaporation. Now these two are very fun things. Now before I move into boiling and evaporation, now understand that I've already placed some videos discussing this effect using Phet simulations, right? I'm going to link that video over here, right? I'm not going to use this link, but I'm going to put in my own link for the simulation that I've run, and all the features that I've discussed. So if previously you were not able to understand the depth of the things that I've discussed in that simulation, now I think you will be able to understand much better once you operate Phet simulations while reviewing this lecture, right? This presentation. Okay, moving on. We have boiling versus evaporation. So what is boiling and what is evaporation? I'm going to come to evaporation a little later, right? For now, I'm just going to start with boiling. So what is boiling? Let's say we have a beaker filled with water, and we put it on a stove, right? And after a certain while, we see bubbles coming from the bottom up, and we see vapors, huge amount of vapors forming on above the surface and leaving the surface of water. So what is boiling? We can simply say that it is the escape of high energy particles. And why high energy? Because we are providing it energy using a heating source, right? Could be any kind of flame or stove that we're using, right? Could be even a heating rod or a heating plate, right? Electric one, or a flame based one, right? Fire. So the escape of high energy particles from the liquid at boiling point. Now I'm just saying liquid, right? Now it occurs throughout the liquid. As you can see, once water starts boiling, you would find bubbles forming on the walls or the bottom, and these bubbles are actually particles with high energy, and these are vapors, right? Vapors of these particles which turn into a gas, right? And when they have a higher pressure than the atmospheric pressure, the pressure that the atmosphere is applying on this liquid, these will start to escape, right? Now this is a very important fact, that the vapor pressure is more than the atmospheric pressure at in boiling, right? In boiling, the vapor pressure is more than the atmospheric pressure. Now the rate of boiling depends on the rate at which heat is supplied. It doesn't depend on anything else much. At least at your level, we are only going to restrict ourselves that the rate of boiling literally depends on how fast or how much heat we are exchanging at what rate we're giving that energy to these particles, right? Boiling does not depend on anything else. For now, at your level, we're just going to keep it to rate of energy, right? Supplied. And if we increase the external pressure, then we need to understand that the boiling point will increase. Now I'm going to dwell on this using some examples, but not for now. I'm just going to compare boiling with evaporation. And why I've given this point, because we're going to relate this point in terms of evaporation, right? How evaporation is different, and why this factor is there. Now this has applications in terms of pressure cooker. We have that in our houses. What we do is that we apply external pressure by locking the lid, right? So that more vapors stay inside. The vapors are not allowed to escape, which exert more pressure onto the liquid surface, causing the vapors which are inside the liquid not to come out. And when they are not able to come out, they push, and they push harder against the vapors which are closed off. Let's say if I put a lid over here, then these vapors are not able to move out of this container, and they will hit the surface as well, causing the pressure on this liquid surface to be increased. which will force these bubbles to stay inside and not come out, right? Causing the temperature of this liquid to rise more than the boiling point. But we're going to restrict ourselves that when we say boiling and boiling of an open container, that then the temperature will remain at the boiling point till all of the liquid is gone, right? Remember this, that the temperature would not change till all the liquid has escaped. Now let's come to evaporation, right? We're going to remove this cross. So what is evaporation? It is just like boiling. It is also the escape of high energy particles from the liquid at any temperature. Now this is the important factor, that this is at any temperature which is below the boiling point. This is not at boiling point, but instead this could be even at room temperature or even slightly above the freezing temperature, but it needs to be below boiling point, because at boiling point we would have boiling and not evaporation, right? And it only occurs on the surface. That means you do not find bubbles when something is evaporating. A crude example would be a beaker of water left over for a whole day. You simply mark the first level before leaving, right? And once you leave it, for a day, you would find the next day that the level has dropped a little bit. And why? Because some of these high energy particles, which are probably absorbing heat from the environment, right? They will take that energy and get released into the atmosphere, right? Causing some of the level of the water to drop down, right? And we can simply check the next day compared to our previous marking, that this was level 1 and this is now going to be level 2, which is lower, and that shows that these particles have escaped. So we can say that it is only occurring at surface. And why we say this? Because we don't see any bubbles over here, right? That shows that something is happening just on the surface. Why? Because these particles can only escape through the surface. They're closed off from the other sides, right? The rest of the sides are closed by this beaker, so only the surface is open to air. So these particles can only escape from the surface, and since there are no bubbles, so we can say that this is only and only occurring at the surface. This is a clear difference between boiling and evaporation, that evaporation occurs at the surface, boiling occurs throughout the liquid, right? Now in case of vapor pressure, the vapor pressure is less than the atmospheric pressure, and that is why this happens below the boiling point, right? At boiling point, we do know that the vapor pressure is more than the atmospheric pressure, and that is why we see huge amount of vapors or white steam forming right above the surface of the liquid, while in this case we may not be able to detect any kind of vapors over here until unless we place some partial lid that will try to condense some of these escaping molecules. And we do see that if we keep a lid with a slight slit in there, you would find some of these water vapors condense on the top, right? And that shows that the water is trying to escape from the surface, while we do not have any bubbles and we do not give any heat to this. So remember, in this case we are not heating up, in this case we're heating, right? So we have heat over here, right? In this case this is only dependent upon ambient conditions. So on what factors does the rate of evaporation depends? How fast something can evaporate? It depends on several factors, but for physics we're going to restrict ourselves to the area, the ambient temperature, and the wind speed. Now the type of material definitely affects the rate of evaporation. If I put honey in a beaker, then I don't think it's going to evaporate that fast. So the mass of the particle, the molecular mass, definitely affects the rate at which a liquid is going to evaporate. But again, as I said, that is more a constraint in chemistry than in physics. So in physics we're just going to restrict ourselves with the area, the ambient temperature, and the wind speed. So greater the area, consider that you take a beaker, you take two identical beakers with equal amount of water in them, you keep one beaker as is, and you spill the other beaker on the floor, right? Now since the ambient temperature is the same in the room, right, the wind is not there, it's a closed off room, there is no wind, So both the water in the beaker and the water on the floor have similar conditions, except the water on the floor has more area, and you would find that after half an hour, the beaker containing water will have probably a minute change in the level, but the water on the floor, that the same amount of water which was in the second beaker, which we spilled on the floor, will be gone. Why? Because the surface area accelerated the rate of evaporation. So if you want to increase evaporation, the rate of evaporation, we just need to increase the area. That's the simplest trick in the book, right? The other way around is the ambient temperature. That means, let's say if you're trying to dry some clothes. So in summers, the clothes will dry faster because the ambient temperature is higher. So that means the native energy that these particles have to escape is greater than in winter. So definitely the ambient temperature also affects. Now third, wind speed. Let's say I have a room in which I have two beakers. Now I'm not going to spill that beaker, right? I'm just going to keep both the beakers intact. They are at same conditions. The ambient temperature of the room is same, except now I'm going to take the other beaker into the other room, which is at the same conditions, except in the other room I turn on the fan, right? And due to the change in the air current, we would find that the beaker in the room that has the fan running will evaporate faster. It would be dried off probably by the end of the day, while the other room in which there was no wind, there was no fan, the beaker will still have some quantity of water left, right? So definitely wind speed really affects. So if you hang out your clothes when it's a bit windy outside, you'd find that your clothes are drying up faster compared to if you hang your clothes inside the house, right? Considering that the temperature and the area is kept the same for both those experiments, right? Now I hope I'm able to clarify the difference between boiling and evaporation, right? Moving on, thermal heat. Now this is the more technical part of this thermal block. I mean, this is the you can say the second last topic before we move into how thermal energy flows from one object to another. So we're going to discuss this numerical understanding of how heat and energy and the temperature works. So let's ask a question. Let's say if you have 1 kilogram of water and 1 kilogram of aluminum, what requires more energy to heat up by 1 degree Celsius? Now imagine we have both of these at 25 degrees Celsius, right? Just at 25 degrees Celsius. And we want to raise the temperature by 1 degree Celsius, that would be 26, right? So which one of these would require more energy? And the answer is actually water. Why? Because water will require 4200 joules of energy to increase its temperature from 25 to 26, while on the contrary, aluminum is not going to require that much energy. It is just going to require 900 joules of energy to raise its temperature from 25 to 26. Now imagine that the mass in this case was same, right? We are using same amount of mass. Mass is constant for this experiment. So before we discuss thermal capacity, or what is thermal capacity, we need to understand we have to have some restraint before we discuss thermal capacity. And in this case, we're keeping the mass same. So what is thermal capacity? It is the amount of energy or heat that an object of a certain mass can absorb before it raises its temperature by 1 degree Celsius, right? So what is thermal energy? So it is all to do with the specific heat capacity of the material. That means, what is now specific heat capacity? This is the ability of a independent material to have its own ability to absorb energy. That means water, since it's taking, as you can see over here, is taking a lot more energy compared to aluminum, even though the mass is the same. That means that water has this something different compared to aluminum. Even though the mass is the same, the chemical properties or the physical properties of the water are affecting the heat exchange in such a way that water will require a lot more energy before it increases temperature by 1 degree Celsius as compared to aluminum. So this, we can say that specific heat capacity is an intrinsic property. And what's an intrinsic property? It's a property that depends upon the atomic structure or the chemical combination of the elements, or how the compound is built, or how it is structured, right? So it's an intrinsic property, so it's dependent upon the type of material we are using. In this case, water requires more energy than aluminum, right? So specific heat capacity of a substance is the amount of energy needed to change the temperature of 1 kilogram, again very important to note, of a substance by 1 degree Celsius, right? So water over here has the highest specific heat capacity. Oxygen would require 918, lead would require 128. That means it is very easy to raise the temperature of 1 kilogram of lead compared to 1 kilogram of water. Now this factor of water needs to be understood, that water has huge applications in terms of heat storing or heat exchanges, right? Now we do know that our cars have radiators that utilize water as a heat exchanger, right? Then we have other heat storing devices. For example, we use water, right? Steam heating for housing, right? So water having particularly high specific heat capacity makes it very useful for storing heat energy and for transporting it for example, in terms of central heating, right? So water has huge applications due to its unique and high specific heat capacity, right? So let's get into the numerical version of this, that what is thermal capacity? It is the energy transferred to a specific mass with some specific heat capacity at a certain temperature, right? So in other words, we can say that E, or energy, right, depends on the product of mass into specific capacity and the temperature that was increased. So where M is the mass in kilograms, C is the specific heat capacity in joules per kilogram per Celsius, right? And delta T, or change in temperature, is measured in degree Celsius and degree Kelvin. And remember, delta T is same for degree Celsius and degree Kelvin, right? Now understand that delta T, only delta T is same for degree Celsius and Kelvin, not T itself. If I discuss a specific temperature, then you need to understand that Kelvin is going to have a different value and degree Celsius is going to have a different value. But when we discuss change in temperature, so let's say if we have water boiling from freezing, so it goes from 0 degree Celsius to 100, right? So that is in degree Celsius, right? In Kelvins, this is going to be 273 Kelvin to 373 Kelvin, right? So there's a huge difference in numerical values in degree Celsius and degree Kelvin. But if you look at the difference that they're having, so what is the difference of values? So over here delta T is 100, that the change in numerical value is 100, and over here again you see that the change is also 100. So we can say that the delta T is same for degree Celsius or Kelvin, right? So it's the same for both of them, right? While individual temperatures would not be the same. So do not make this mistake to take degree Celsius directly as Kelvin. You need to have the conversion, right? And we did discuss conversion in the classroom, right? So delta T is the change in temperature, which would be same for Kelvin and degree Celsius. Now let's have a numerical value, right? A numerical problem. How much energy needs to be transferred to raise the temperature of 2 kilogram of water from 20 degrees Celsius to 30 degrees Celsius, right? So how much is delta T? That is from 20 to 30. So delta T would be change in temperature, and that is 10 degrees Celsius. We have increased the temperature by 10 degrees, right? And how much energy is required to increase the temperature? So we have mass over here. So we're going to take M, right? We're going to take C, and we're going to take delta T, right? So mass of water is 2 kilograms, right? We can also use volume instead of mass. So don't get disturbed if I give you volume in terms of question, right? So I may not give you directly the mass. I may give you volume, and you need to remember that density of water is to be remembered, right? That is 1000 kilograms per meter cube, and that is in per meter kilograms per meter cube, not in grams per centimeter cube, right? So understand the difference in units. So when we're talking kilograms, we need to understand, we need to take density in kilograms per meter cube, right? So this is mass over here, which can be extracted from volume if I give you volume in the question. Then we have the specific heat capacity. For water, you need to memorize this value. Now for Cambridge exam, you need to understand the specified value is 4200 joules per kilogram and degree Celsius, right? Over here I'm using 4181, that is a more exact value, but for Cambridge we use a rounded off value of 4200, right? And the change in temperature is from 20 to 30. So we have 2 into the specific heat capacity into the change in temperature, giving you 83.62 kilojoules. That means you would need to provide 83,620 joules of energy to raise the temperature of 2 kilograms, that is roughly 2 liters of water, by 10 degrees. So that shows that water can absorb a lot of heat before it heats up itself. I mean, before it changes its temperature, right? So water can absorb a lot of heat, and that is why we use water in heat exchangers, because it can absorb a lot of heat before it starts boiling, right? So if you think boiling water is an easy job, no, it actually consumes a lot more energy. If you're boiling any other material, any other liquid, then we would not be giving that much energy, right? Water is going to take the highest amount of energy. So what is thermal capacity now, right? Now this was specific heat capacity and the energy associated with specific heat capacity. Now what is thermal capacity? It is the amount of energy that every 1 degree Celsius of temperature would require to be increased for a specific amount of mass. That means now I can simply draw this conclusion that the thermal capacity, now do not confuse this with this thermal energy. This is thermal energy and this is thermal capacity, right? This is how we measure that how much energy is required for a specific mass, right? So thermal capacity is actually the amount of mass that you have into its specific heat capacity. That this is the amount of energy that you would require to increase its temperature, right? So if there is 3 kilograms of water in kettle, then the thermal capacity, that the amount of energy that it may absorb before it changes its temperature even by 1 degree Celsius, would be 3 times, which is the mass, multiplied the specific heat capacity, and that is the amount of energy that it would require to increase its temperature by 1 degree Celsius. So every 1 degree Celsius change in energy would require this much amount of energy to be supplied to this much mass, right? And this is a mass dependent quantity. Remember, this is a mass dependent quantity, right? So moving on, how we can measure specific heat capacity. Now this is an experimental problem, right? I think one of these simulations is also available in the Phet simulations, but I'm not going to discuss it for now. I'm just going to get into the apparatus and how this experiment is done. So imagine we have two blocks in which we have a solid heater, right? A solid block of metal in which we have an immersion heater. We have placed the heater inside it, and this is an insulating container in which this metal is placed, and then we have this thermometer, right? And then once we turn on this electric heater, we do know the amount of energy, electric energy, that we're giving. That means we can easily account for the amount of energy. Again, change of energy from electric to thermal, we can simply calculate using the amount of current or the power, electric power we are supplying to this heater. That would be equal to the amount of energy given by this heater to this solid block. Now the similar experiment is being done on this liquid, in which we have to add this stirrer. And why this stirrer? Because we need the temperature to be consistent throughout the liquid. We do know that hot liquids tend to move upward and the colder liquids tend to move downward, right? Fluids. So water is a fluid, so we need to understand that if we don't stir it up, then the temperature on the top would be different and the bottom would be different. And wherever our thermometer bulb is, which is at the lower end, we won't be able to get the exact reading or the accurate reading for temperature. So keep this idea in mind, that stirring is really important if you're doing this experiment for liquids. For solids actually transfer heat equally in all directions, so we don't have this issue of stirring in solids. But in liquid, we need to understand that we need to stir the liquid so that the temperature throughout the liquid is consistent while we're increasing it, right? And we also need to put a lid. Why? Because if we keep on increasing the temperature, we do know that increase in temperature increases the rate of evaporation. So some of the energy will be released out with the escaping molecules. So we don't want these molecules to escape, so that the energy of this container remains at a constant level, and we have an accurate measurement of temperature. So beaker contains 0.7 kilograms of water. It's an immersion heater of 200 watts. Switch on for 200 seconds, right? We do know power is actually energy over time, right? How much energy is given for a specific time. So we can calculate energy from this, which is equal to power into time, right? We have the power, which is 200, and we have the time, which is also 200. So the energy is going to be and remember, watts correspond to joules of energy, right? So it is going to be 2 into 2, 4, and with 4 zeros, that is going to be 40,000 joules of energy, right? That is what we have supplied to this 0.7 kilogram of water. And the temperature of the water rises by 12 degrees Celsius. So the delta T, as they're saying, rises by 12 degrees Celsius. That means this is delta T and not temperature, not a specific temperature, right? It's the change in temperature. So the delta T is 12.5, right? So they're asking us to find the specific heat capacity, or symbol C, right? So we do know that change in energy, delta E, is equal to m C delta T, right? And we want to find this C. Now we keep C on one side, right? And we're going to take rest of these, since these are multiplied with C, on the other side they will be divided. So due to delta E, change in energy, which is this value, right, divided by the mass into delta T, right? And that should be equal to, let me just pull out my calculator, right? No, we're going to keep for now, right? We're going to pull out our calculator. We're going to use this. So it's 40,000 divided by 0.75, which is the mass, further divided by 12.5, that is a change in temperature. So that would be 42, right? That would be roughly 42. That's what I was just telling you, that as a whole, that is 4266 joules. Now why extra energy is there? Because some of the extra energies is absorbed and is now calculated. There must be some explanation to this change in value compared to what we are using as 4181 joules, which is the exact value, right? There must be some inaccuracy, and that inaccuracy you need to discuss as a factor, right? So this is the solution to this problem, right? The actual value for the specific heat capacity of water is this. The method described does not make any allowance for heat loss to the surrounding or the beaker, right? So so that means some of the extra energy is there. And why is that so? Because some extra energy is there because, as I told you, that this is a closed lid, so water vapors will collect on the top and they will exert some extra pressure onto the liquid, which would technically require more energy for this water to be heating up. So there would be some change, some increase in the value of energy. So don't think that this is a wrong value. This is also accurate considering the experiment, that it's a real experiment. uh, this is more of an idealistic case, but that's what we do. Okay, thermal capacity. What are the applications? Using high specific heat of capacity, shelter heating is done, in which we have a boiler, we have radiators that give hot steam in our room during winters, heating up our room, and then the cold or the water that has reduced its energy, has radiated its energy, is sent back into the boiler. So it's a cycle. So only steam gets out, and the hot water is pumped back into the system. So this is how the central heating works. For large scale structures like offices or buildings or towers, we don't have these kinds of system in Pakistan, but you get to see these in movies. You find that even in some modern application buildings, we have these boilers available in some hotels or some hostels of some well designed buildings, but casually we don't have these in our houses because we use dry heating systems, which is like pure burning. Or then other than that, we have electric heating systems. We actually don't use these radiator systems, right, in the houses, because this actually requires a lot more technical approach into devising this system for your house, right? Okay. Even in the car we have this the more crude example would be the car, in which we don't allow the heat to go out of the system, but we simply run that uh, steam inside, and we cool it using a fan, which prevents boiling of this, which cools the hot water down and then sends the cold water back into the engine, and the engine is acting quite like a boiler, which is heating the water up, and this cycle continues. This is the cooling system of a engine drawn, right? So the water, uh, you know the as we do know that colder water would go down and hot water will move up. So we're going to simply use this as that we push in hot water from the top, we allow it to fall down through gravity, and as a result it is cooling down, and colder water will also move down, so it will go through the lower pipe, go through the engine, heat up, and get back through and get back into the cycle. For this we have this pump which forces the water to run through this closed loop system, right? And this is due to the high specific heat capacity of water that we have discussed previously, right? Okay. That's the end of this lesson. The next one is going to be regarding radiation, convection, and conduction, and that is a very tiny little topic. So before we get into this, so understand that you need to go through all these simulations that I've discussed previously. Phet simulations do run this experiment, explore how gases and liquids and solids expand and behave under temperature changes, and how energy is being transferred. I've placed some of those tutorials in the video section, so go through those again if you have already gone through those. So I think now you're going to have a much better understanding of what I was doing with those experiments. If you were not able to grasp those ideas in class, I think now you will be able to apply those these ideas to those simulations that I was running. Thank you.